Hey there. We're dealing with forces literally every second of every day. Pushing a door open, picking up your coffee, heck, even just sitting in your chair right now. But what is this invisible thing that makes everything move? Well, today we're going to dig in and find out what really makes things go.
So I want you to think about this for a second. Imagine you're riding a bike. To keep going, you've got to keep pedaling, right? The second you stop, you start slowing down. It just feels intuitive that motion needs constant effort. But is that really what's going on? That's the big puzzle we're going to solve today.
All right, so to get to the bottom of this whole bicycle thing, here's our roadmap. First up, we'll nail down what a force even is. Then, we'll check out the 5 different things a force can do. After that, and this is a big one, we'll get into balanced versus unbalanced forces. And that's what's going to lead us straight to the truth about motion.
Okay, let's kick things off with part 1. What is force? I'm calling this the invisible push and pull because really, that's what it all comes down to.
In physics, the definition is actually super simple. A force is just a push or a pull on something. That's it. That's the whole definition. Every single thing that makes an object move, or even just tries to make it move, boils down to either a push or a pull.
Let's take a super clear example. Pushing a ball, you kick it, right? Your foot gives it a push, and bam, the ball, which was just sitting there, takes off. That's a classic push force in action.
And of course, the opposite is just as common. Pulling a drawer. To get it open, you gotta pull it. You're applying a force to move it from in to out. Simple as that.
But what about something a little more complex, like twisting a cloth? It feels different, doesn't it? But if you break it down, you're really just pushing with one part of your hand and pulling with another in opposite directions. So even something that seems complicated, like a twist, is still just a combination of good old-fashioned pushes and pulls.
Okay, so we've established that a force is a push or a pull. But here's the thing. You can't actually see a force. It's invisible. So how do we know it's there? Well, we see what it does. And that brings us perfectly to our second section, the 5 effects of force.
So, when a force acts on something, it can do one of 5 things. It can get something moving, it can stop something that's already moving, it can make it go faster or slower, it can change its direction, and it can even change its shape.
All right, number 1 is probably the most obvious. A force can make a stationary object start to move. We've already talked about kicking a football on the ground. That's a perfect example. A force comes along and gets it going. Next up, a force can stop a moving body. Think about applying the brakes in a car. But this is really just a specific case of our third effect, changing speed. When you brake, you're applying a force to slow the car down, all the way to 0. And when you hit the gas, you're applying a force to speed it up. So starting and stopping, they're really just about changing speed.
A force can also totally change the direction of a moving object. I mean, look at a cricket bat hitting a ball. The ball's flying in one way and whack! The bat applies a massive force that sends it in a completely new direction. But here's something cool. That same hit also shows our last effect. For a split second, the force of that bat literally changes the shape of the ball, squishing it before it flies off. Pretty amazing, right?
All right, now we're getting to the real heart of the matter, section 3. We have to talk about the difference between balanced and unbalanced forces. Seriously, this one idea is the key to unlocking this whole motion puzzle.
So, what's the difference? It's actually pretty straightforward. With balanced forces, all the pushes and pulls acting on an object completely cancel each other out. The total, or resultant force, is 0. Nothing changes. But with unbalanced forces, they don't cancel out. There's some leftover force in one direction, and that is when the magic happens. That's when things move. Okay, let's make this real. For balanced forces, just imagine a super heavy box. You're pushing on it with all your might, and nothing. It doesn't move an inch. So what's going on?
Well, it turns out there are a bunch of forces at play. You've got your push going forward, right? But friction is pushing back just as hard. They cancel out. And at the same time, gravity is pulling the box down, but the floor is pushing right back up with the exact same amount of force. So those cancel out too. All the forces are in perfect balance. The result? 0 change. The box stays exactly where it is.
And this leads us to the most important rule of the day. When unbalanced forces show up, they cause a change. They can make something start moving, stop moving, or change direction. It's the unbalanced force that's the agent of change. Okay, so now let's switch gears. Instead of that heavy box, imagine you're just pushing a little toy car.
You give it a little push, and it zips across the floor. So, what's the difference here?
Well, this time, the force from your push is way, way bigger than the tiny little bit of friction from the wheels. So the forces are unbalanced. There's a net force, a leftover push that's greater than zero. And that's what makes the car move. It's that imbalance that creates the motion.
And that right there brings us to our final section. It's time to put all of these pieces together and finally, once and for all, solve the bicycle puzzle.
Okay, let's get back on that bike. We just said that you need an unbalanced force to change motion. So why on earth do you have to keep pedaling just to keep going at the same speed?
And here it is, the big reveal. And it might seem a little weird at first. To keep your bike moving at a steady, constant speed, the forces have to be balanced. Yeah, you heard me right. The push forward from your pedaling isn't winning. It's perfectly matching and canceling out the push backward from things like air resistance and friction. Your pedaling isn't causing acceleration, it's just maintaining a perfect state of equilibrium that lets you keep cruising along.
So let's wrap this up with the most important takeaway. You need an unbalanced force to change things, to speed up, slow down, or turn. But to maintain a constant speed, you need balanced forces. That idea we all have that motion requires a constant push, that's just an illusion created by the friction we have to fight against every day here on Earth.
Which leaves me with one last question for you to chew on. Picture an astronaut out in the vacuum of space. No air, no friction. She gives a wrench a little push, and it just drifts away at a constant speed. So, based on everything we've talked about, what would it take to stop it? Think about that one. Thanks for tuning in.